Hello, hello guys. So you're welcome to this. You're welcome to this lecture. This lecture is going to look at a three of groups. We want to look at subgroups, especially in this video. Okay, and then later on we'll look at some other stuff. Okay, so we'll look at subgroups. And then later in some other videos, we'll look at group isomorphisms, homomorphisms, and then maybe the kernel of a homomorphism. All right. So that is the plan. So what is a subgroup? Well, if you have a non-empty subset H of a group G, right, under this operation, then H, which is a subset of G here, is called a subgroup of G if the elements of H form a group under this operation. Okay. So for H to be a subgroup, H first has to be a subset of G. And if you take the elements of H, right, they must form a group under the same operation. This is important. So you can't have different operations, one for the subgroup and the other for the group. They must use the same operation. Okay, so that is the definition of a subgroup. Well, so if you take G itself, right, G itself, you can consider it as a subgroup of itself, but that is called an improper subgroup because G is not a subset of G. It's an improper subset, right? All other subgroups are proper subgroups. Now, you can actually show that E, the identity element in G, if you take that element alone, is actually a subgroup. And you can prove that it satisfies all the axioms for a group. But it is a subgroup because the set containing only E is a subset of G. Okay. Now all other, but it is called a trivial subgroup because it has only a single element. And all other subgroups are said to be non-trivial. Okay. Now this is a notation, right? When you see H is less than or equal to G, this is a notation to mean that H here is a subgroup of G. Is the same as that, right? If H is strictly less than G, means that H is a proper, right? A proper subgroup of G. In other words, H is never equal to G. Okay, so these are notations that you will come across doing abstract algebra. Okay, so there are two theorems here that we are going to look at, and they are very important because we'll apply them in some examples and other theorems that we'll look at. So it's important to pay attention to them. Sometimes they are used without referencing them, right? When you are asked to prove that something is a subgroup, in fact, some theorems will go straight away to prove using these theorems, theorem 3 and theorem 4, but most especially theorem 3, without telling you that we're actually going to apply the axioms here to show that it is a subgroup. Okay, so pay attention to that. So theorem 3 says that let H be a non-empty subset of a group G. Okay, when I say group G without bringing star, it's implied that G here is related to some binary operation star. Okay, so H is a non-empty subset of the group G. Okay, then H here is a subgroup of G if and only if the following two conditions are satisfied. For all A and B in H, AB is A star B, A operation B, right? We remove it. AB here is an element of H. And if I pick any element A in H, it has an inverse which also belongs to H. Okay. So this is if and only if. So if H is a subgroup, I expect these two conditions to be satisfied. On the other hand, or conversely, if these two conditions are satisfied, I can conclude that H is a subgroup. And so often to prove that something is a subgroup, you can verify these two conditions. And if they hold, you can just conclude that yes, it is a subgroup. Okay, so how do we prove this? Let's prove this one. The first part is easy. We can let H be a non-empty subset of the group G. This is given to us from the theorem. And we suppose that H here, so the first part, we want to suppose H is a subgroup of G. Okay, well, by definition, a subgroup really is a group. Okay, don't forget that a subgroup is a group. The difference is that that subgroup, the set of the subgroup is a subset, right, of the main group. Okay, so it is a group. Well, since H here is a subgroup and therefore a group, well, this is easy to verify these ones, right? Since it is a subgroup, if I take any two elements in it and operate on them, I should get an element that is in H, because the binary operation there, or if you like, the operation there is a binary operation, right? Again, I'll show you some of the details. Again, this one is also easy to prove. If H is a subgroup, right? Then it is a group, and therefore every element in it must have an inverse, right? So this must also hold. So this is trivial. The first part is trivial. If you assume that H is a subgroup, these are easy to show. I'll show you some of the details here. So you can let, for instance, B denote the inverse of A in H. It must have an inverse because we are supposing H to be a subgroup. So it has an inverse. So if I multiply A and B, I should get E, which is the identity element in G, right? Well, we have proved already that the identity element is unique. There's only one identity element. So if H is a subgroup, it must have an identity element, and that identity element must be the same identity element as G, right? So AB is equal to the identity element E in G. Now, since the identity element of H is the same as that of G, right? E must belong to H, right? Okay, so if this is the case, it means that B here has to be the inverse of A. So B has to be equal to this. So the inverse of A is in G. All right. So this is this A inverse is an element of H. Okay, because E here is also in H. Remember, and A and B are elements of H. So A inverse is in H. So so I is satisfied, right? The inverse is there. Okay, so this is straightforward. The converse is more interesting and more trickier, right? Now we want to assume these two conditions are satisfied, these two conditions hold, and then prove that H is a subgroup. Well, to prove that H is a subgroup, what really we want to do is that we want to prove that all the axioms for a group are satisfied in it, right? That is what we want to do. We want to show that there is an identity element. If I take any element, it has an inverse, and then associativity also holds. So I need to show this three to show that H is a subgroup. All right. Okay. So we'll assume, conversely, we're going to assume that these two conditions hold. Okay. And then we'll use that to prove that H is a subgroup. So suppose these two conditions hold, and let X be an element in H. Okay. Remember, H is non-empty, so it has elements. Then this condition says if there's an element, there must be an inverse, right? Then X inverse must be in H. Okay. Well, the first condition says that if I have two elements in H, the product must be in H as well. Well, I have X that is in H. I also have X inverse that is in H. So at least I have these two elements in H. If I multiply them, find the product of them, or find operation, this must be in H. But X star X inverse is the identity element, which means the identity element is in H. So I have shown that H has an identity element. That is fine. Okay. It also has what? An inverse. So that is good. The only thing left is associativity. Okay. So let A, B, and C be elements of H. Then A, B, and C are in G as well, because H is a subset of G. So A, B, and C must be elements in G. Well, in G, the operation is associative, right? Therefore, if I take A, B, C, this has to be equal to this. These are basically applying the operation in G. Okay. All right. So that also means that elements in H obey this law. Therefore, associativity in G, right, transfers to the associativity in H. Okay. So associativity is satisfied. H has an inverse for every element. H has an identity element. Therefore, H is a subgroup. Okay. So we have proved this theorem. Good. The other important theorem is this one. Okay, this is this is a subset H of a group G is a subgroup if and only if H is non-empty. Okay, and whenever X, Y is in H, then X, right, times Y inverse is also an element of H. Okay. So sometimes it's convenient to use this one to prove that a subset is a subgroup, okay? But for most times, theorem 3 is used. But let's look at theorem 4, okay? So we want to first, as we did for the other one, we want to first assume that H is a subgroup, and then, right? And then show that, well, it is non-empty, and that this is satisfied. If I take any two elements, it's satisfied. And then conversely, I want to show that if H is not empty and this is satisfied, H is a subgroup. Okay. So the first part from the theorem, we let G be a group and H is a subset of G. Now I want to suppose that H is a subgroup of G. All right. Again, remember, a subgroup is a group. So all the axioms for a group hold in H. Okay. So let's suppose first H is a subgroup. Then it means that it must have an identity element, right, in H. So H is not empty. Okay. It's not empty. Good. Now we want to prove this side now. Let X and Y be elements of H. Remember, H is a subgroup. Therefore, every element must have an inverse as well. Okay, so Y must have its inverse, which means that Y inverse is an element of H because H is a subgroup. And so I can also multiply them, right? If it's a subgroup, if I take any two elements and multiply them, right, and operate on them, the result must be in the subset or in the subgroup, right? So if I take X, which is in H, and Y inverse, which is in H, multiply them, the result must also be in H. Okay, so if I assume that H is a subgroup, I can show that it is non-empty because it contains the identity, and I can show that this hold. So this first part is proved. Good. I want to prove the converse. All right. Now I want to suppose that H is non-empty. All right, and that when I pick two elements in H, okay, X times Y inverse also belongs to H. Okay. So it's not empty, and and that this condition also holds. So using this, the fact that H is not empty, and this, I want to prove it's a subgroup. Again, to prove it's a subgroup, basically I want to prove it's a group. Associativity, there is an identity, and every element has an inverse. Keep that in mind always. Okay, good. Now, when X, right, I'm given these conditions already. Okay, X and Y, and this holds. Well, let Y here be X. If Y is X, right, if I multiply X by X inverse, I'm going to have it belongs to H because this belongs to H. We know this is given to us. All right, so X inverse belongs to H, but X inverse is the identity element, which means the identity element is in H. Okay, so the axiom for identity, that is satisfied. We have that already. Okay. Now, in here, if I replace, if you like, X here, E, remember, is in H. So I can replace X here with E. If I do that, I'm going to have E times Y inverse, but E times Y inverse will give me Y inverse, right? Okay, this belongs to H. Therefore, Y inverse must belong to H as well. Okay, so the inverse belongs to H. Good. Now I want to show that if I take any two elements in H, right, I get an element that is also in H. If I take two elements and multiply them or find a product or operate on them, the result will also be in H. Okay, to show that the operation there is, if you like, a binary operation. I can show that. So if I take X multiplied by Y, I'm going to have X. Remember, Y inverse, the inverse of the inverse gives you Y. Okay, we have shown this already in some of our lectures. So X times this is true. Now you can replace this guy by some B, right? So I have X B inverse, well, where B is equal to this, which is in H anyway, right? So X is in H, B inverse is in H. Therefore, the product X times Y is in H, okay? So we have shown that the operation there is a binary operation, okay? So we have identity, we have inverse, it's a binary operation. What is left is to show associativity, okay? Now, associativity, as before, is a straightforward. It's guaranteed because H is a subset, right? It's a subset of G. And since associativity holds in G, for all the elements in G, it must hold for the elements in H as well. So we have proved that H is indeed a subgroup of what? Of G. Okay, so basically that is what we have. That is what we have shown. Good. Let's look at some examples. These are, if you like, trivial examples. Okay, we know that the set of integers, the set of integers, and the set of real numbers, right, and the addition are groups. Okay, when we dealt with groups, we saw these examples. However, Z here, the set of integers and addition, is a subgroup of the set of real numbers and addition because, right, Z here is a subset of R, right? A set of integers is a subset of the set of real numbers. Okay, also, this group, well, this group here, the group of positive rational numbers and the multiplication, this is not, it is not a subgroup, right, of the set of real numbers and the addition, right? Even though this guy here, the set of positive rational numbers is a subset of this, this is not a group of a subgroup of this because the operations are different. This is multiplication and that is addition. So you can go back and look at the definition of a subgroup again. If H is a subgroup of G, the elements of H, okay, must obey the axioms of a group under the same operation as G. Okay, so you can't have different operations, as I mentioned before. So you can look at the definition. Okay, here, Q, the set of positive rational numbers under multiplication is a subgroup of the set of positive real numbers under multiplication, right? Because Q plus here is a subset of R plus. Okay, now, but R plus here is a subgroup of this set. This is because R plus is a subset of this set. This set is a set of all real numbers minus 0, right? The only thing that is removed is 0. Otherwise, all the elements of real numbers are in here. But here you are considering only the positive ones. So this is definitely a subset of that. And therefore, this is a subgroup of the set. Okay, so these are some kind of trivial, if you like, subgroup. The next example is more interesting. Okay, so let's do that and then we'll end this video. So pay attention to this. These are so many interesting elements buried in it. Okay, let G be a group and H a subgroup of G. Good. Now for a fixed element A, which is in G, let's define this A inverse H A, right? This is some kind of a subset, right? This defined by this A inverse H A, where H here is an element of big H. All right. So the elements, all the elements in this subgroup, well, we want to show that it's a subgroup, all right, of this set here. The elements of this set are defined by this. So you pick an element in H and you do this product. All right. This product here, this thing here is an element of this set. If I pick another H, another whatever, let's call it Q. Q is in H. If I put Q in here, this is another element of this set. Okay, that is what it's saying. We want to show that this set here, all right, is a subgroup of G, right? It's going to use the operation of G. So we want to show it's a subgroup. Well, to show it's a subgroup, remember, you can go back to this. Theorem 3. To show that something is a subgroup, we can show that if we pick any two elements in it and find a product, the result will be in H, right? If H is a subgroup. And also if we pick an element, I can show that the inverse is also in H. If I can show these two, then I have proved that H is a subgroup. So we are going to use that in this example. Okay, so that's basically what we're going to do. Good. Now, let H be equal to this. This is given to us in the theorem. Now for some fixed A in G, right? Okay, from the theorem again. Now, since E belongs to H, okay, H here is a subgroup of G. So E here is, of course, an element of H. So I can pick, remember, H here, I can pick any element in H and plug it in here. Now, E is an element of H, so I can basically put it here, all right? And I'll get E to the A to the negative 1, EA has to be an element of this set, right? Because E here belongs to H, okay? Hope that is clear. Good, but know that all of this belongs to the set. Well, you can rewrite, you can reduce this, or you can compute this. If you compute this, right, you end up with E, right? Because E inverse times A inverse times E will be A inverse. A inverse times A will give you E, which means that E is in fact an element of this set. Okay? That's what I have shown here. Okay, so we know that the set contains an identity, contains the identity element, which means it is not empty. Remember the theorem says H is a non-empty set and all of that. So it is not empty. Good. Now we want to show that if you pick any two elements in the set and multiply them, the result will be in what? In the set. Okay, according to theorem 3. So take elements X and Y belonging to this. Well, what does it mean for elements to belong to this set? What that means is that if I pick some H, let's call it H1, in here, I'll get this element, let's call it X. If I pick another element, let's call it H2, I'll get this element, Y. So X and Y belonging to this set means that I pick two elements, put them in here, and this is one of the elements, okay? So this means that X will be equal to A inverse H1A, and Y is equal to this, where H1 and H2 belong to H, okay? That is what it means to be an element of this set. So this is important. Good. Now, if I multiply them, the two elements, right? X is given by this, so I can have that. Y is given by this, I have this. Well, the A's and the H's are all elements of a group or a subgroup, so associativity holds. So I can regroup them, okay? I can regroup them like this. This is E, okay? So if I multiply E by any of the elements, I get back the elements. So this is E multiplied by this, you get H1. So you have H1 and H2, okay? Note that H1 and H2 are elements of a subgroup, okay? So their products must belong to H as well, okay? Let's call their product some L. So I have A inverse L A, where L here is equal to this. And of course, I just repeated what is there before. So L here, which is H1 times H2, must be an element of big H, okay? Good. So what this means is that since this guy here, L here, is an element of H, the whole of this here, okay? In other words, X times Y is an element of the set, okay? So remember theorem 3, okay? If you can show that you take two elements and multiply them and the result is in H, and also if you can find that if I take an element in H and its inverse is also in H, if I can prove those two, then I can conclude that H is a subgroup. That is what we are doing. Here, the first part is this, or if you like, yes, the first part, right? The product belongs to the set. So this is done. Now, if I take X in the set, right, take the inverse of it. The inverse of it will be the inverse of this, right? X is given by this guy. So the inverse is this. Remember, okay, so let me go back here and remind you of something we did before. Remember, we said that if I have this, okay, remember this, we said if I have X star Y inverse, this comes first. I'm going to have y inverse star x inverse. Remember that. So it is the y that comes before this. Okay. So here you can do the same thing. This first h1a inverse star or dot a inverse. Well, right? A inverse will just be A. You see that? Now, H1A inverse, I reverse it again. This means that I'm going to have the A inverse first before H1 inverse and then multiply by A. Okay? Good. So that is what I have here. If you take X inverse, you end up with what? A inverse, H1 inverse, and A. Remember that A inverse, of course, belongs to G. A belongs to G, whereas H1 inverse belongs to H, because H is a subgroup, right? It has an inverse. If I pick an element, it has an inverse. So this, of course, belongs to the set. In other words, X inverse belongs to the set, okay? Since H1 inverse is in H. Therefore, this is a group, is a subgroup, right? It is a subgroup because those two conditions from theorem 3, those two conditions are satisfied. Okay, good. So basically that is it for this this example. Okay, I will entreat you to go over it and try to understand it. It has so many interesting things in this. If you are confused about anything, let me know. Okay, so the next lecture will cover group isomorphisms and homomorphisms and all the isms. Okay, so I'll come your way again later on. I'll stop this for now.